Welcome back. We are in our energy unit, and this is lesson 3 in our energy unit, and we're talking about all things electricity today. In previous lessons, in lesson 1, we talked about different forms of energy, so electricity was one of those forms. And then in lesson 2, we talked about how energy can transform from one kind to another. And it does this because the law of conservation of energy says the energy can't be created or destroyed, but it can change form. So we looked at some examples of how that works in real life. And then I told you we were going to start to do a deep dive into some different forms of energy. So we're starting today with electricity, and then we'll move into magnetism, and then we'll just go through all the different forms of energy. Nuclear energy and chemical energy, we touched base on those, and I gave you a definition and some examples in lesson 1, but we are going to save those forms of energy until we get to chemistry. But all the other different forms we're going to talk about in this unit. All right, so by definition, electricity is the flow of electrical charge, which we call electrons. And we're going to talk about this a lot more when we get into our matter and atomic structure lessons, which is going to be part of our chemistry unit. But you do need to know, you need to have this background information before we get into electricity. All matter is made up of atoms, and these atoms consist of 3 particles. So you can have negatively charged electrons, which is what we're focusing on today, and then positively charged protons, and then neutral neutrons. And what happens is when the electrons in an atom start to move, we have what's called electricity. So another thing to note about electricity is this a secondary source, which means it comes from primary sources such as like coal or fuel, natural gas, oil. Electricity is one of the most widely used forms of energy, which is sort of why we're starting here in this lesson, because it's something that we're familiar with. All right, so what I want us to do is pause the video, and I want you to, in your notes, just jot down 5 ways that you use electricity on a daily basis. Now, I'm sure you could think of way more than 5 examples, but maybe you put some of these examples. If you ate breakfast this morning and it was a hot breakfast, perhaps you had to heat that breakfast up, or if you are watching this video on a cell phone, it's working because of electricity. So electricity is something that we definitely use, so it's important that we kind of understand how it works. So there's a lot of different moving parts to electrical energy and electricity. So we're going to start with just a brief overview, and then we're going to move into static electricity and then current electricity. So the flow of electrons through a closed circuit is what generates electricity that will power a device. So here in my picture, if I have a light bulb that's being powered, and you can see those little negatively charged particles. Those are electrons that are moving from the power source, and they're creating what we call a closed circuit. And as long as we have a closed circuit, electricity can flow through and power the light bulb. So an example of this in our homes or at school would be flipping on a light switch. So when you flip on a light switch, you actually close the circuit, and that creates that flow of electrons that powers your lights. So the question here says, what do you suppose happens to the electron flow when the circuit opens? So you can see in this picture here that when the circuit opens, the electrical flow stops. So when you have an open circuit, since the path is not complete, the light bulb will not be powered. So an example of this would be when you turn off a light switch. When you turn off the light switch, that opens the circuit, and so you don't have that continuous flow of electricity to power your lights. Now we're going to focus on 2 types of electricity. We're going to start with static electricity, talk about what that is, some examples, how that works, and then we're going to go into current electricity, and then we're going to camp out here for a good bit of time. So static electricity is something that you are probably familiar with if you've ever jumped on a trampoline and then tried to get off and you touch the metal bar on the side. You may have experienced a shock, or if you have jumped out of your car and then touched a gas pump or touched the side of the car, you may have gotten shocked. And if you have, then you have experienced static electricity. So by definition, static electricity is the accumulation of excess electric charges, which remember we are calling electrons, on an object. All right, so a little bit of background information before we talk about the law of attraction. Normally, in an object, the number of protons and electrons balance. So I just mentioned that all matter is made up of atoms, and those atoms have protons, neutrons, and electrons. Well, normally the number of electrons and the number of protons are equal. So we say that it's balanced, or it doesn't have a net charge. Electrons are really, really tiny, and they loosely adhere to the atom. So when you rub two objects together, electrons sometimes can easily be transferred, or they can migrate from one surface to another. And what that creates is a net charge. Basically, you'll have more electrons on one surface than you do on another. And so, looking at the screen, we have something called the law of attraction, which shows up a lot in physics, but basically it says that opposite charges attract and like charges repel. So we can see here in the picture that you have a negatively charged electron, a positively charged proton. Naturally, through the law of attraction, they're going to want to attract to one another, come together. When you have two negatives or two positives, and they come close together, they're going to want to repel one another. So that concept can be used to understand static electricity and what happens with static electricity. So if you've ever pulled your clothes out of the dryer and they've kind of been stuck together, that's because opposites are attracting there. So you have some garments that have a net positive charge, some garments that have a net negative charge, and through the law of attraction, they're trying to adhere to one another. All right, so what causes static electricity? We just said that most objects do have a neutral charge, which means the same number of protons as electrons. And you can see here in the picture of the hand and the balloon before you rub them together. This is what we call an equal charge. So they're at equilibrium, the same number of protons as electrons in the balloon, the same number of protons as electrons on the hand. Now, after you rub them together, you notice that some of the electrons have left the hand and moved to the balloon. So the balloon has a net negative charge and the hand has a net positive charge. Now, what might happen is if that balloon were to get near something that has a net positive charge, it will try to stick to or attract to the net positive charge. So what we have there sometimes is a static discharge. Sometimes they'll just stick together, and sometimes they'll actually discharge. You'll have a spark. So when one object rubs against another object, electrons are transferred. We just looked at that in the balloon hand example, and then both of the objects become charged. And when an object becomes charged, the charge is neither created or destroyed. So here we see another law of conservation. This is called the law of conservation of charge. The charges can be transferred, though. Right, so here's a little animation. So we can see here that the doorknob has a net positive charge. The person or the hand has a net negative charge, and so you can see a static discharge happens here because those negatives are attracted to those positives. Now, I don't know if you've experienced this, but you can actually have a static discharge between two objects that do not touch. So this person's hand could get a shock even before it touches the actual doorknob. We call that charge through induction. So when two objects come together and a static discharge occurs without touching, that's induction. And I'm going to remind you of that. We're going to get that in our notes in just a second. Another example, if your hair has ever stood up when you rubbed it with a balloon, or even I know in the winter sometimes when I brush my hair really fast, my hair will actually follow my hairbrush. That's the same thing. Static electricity, you have a transfer of charges. One object has a net charge, and then through the law of attraction, those net charges are trying to find their opposing charge. I do want to point out we have a vocabulary term here, conduction. So I mentioned earlier that induction happens when charges come together without touching. Conduction happens when the charges come together between objects that actually touch. So a great example of this would be clothes sticking together in the dryer. If you pull out two pieces and you have to peel them apart from one another, that is conduction. They're actually touching one another. Another example of induction, charging without touching, is is lightning. So lightning happens when you have clouds moving up in the sky and a transfer of charge happens there. So if you have a cloud with a net negative charge and it gets near something that has a net positive charge, they're going to want to attract to each other. So the cloud doesn't have to come down and touch a tree for it to get struck by lightning. The charges will actually jump to one another, and we see it as lightning. All right, so if you are in class with me, you are going to do an activity where we look at the difference between friction, conduction, and induction. If you are just watching this video virtually, then you will need to jot down these definitions and then pause the video and do a quick Google search of examples of friction, examples of conduction, and examples of induction, because you're going to need to know some examples. On your test and on your next quiz for me, you are going to need to be able to look at examples and say, oh, that's an example of conduction, or that is an example of friction. So be sure you jot down these definitions and you know some real life examples of each of these. All right, let's jump into current electricity. So we just talked about static electricity, and now we're going to look at current electricity. And I'll give you just a second to fill in your notes here, but current electricity is the flow of electrons through a circuit. We've mentioned that earlier. We do know a circuit is a complete closed pathway for electricity to flow, and we know that if that circuit is not complete or not closed, then electricity will not flow. And then we need to know the definition for a conductor. So a conductor allows electricity to flow through it easily. Remember, all metals are great conductors of electricity. Here we have a specific form of metal, copper. You also need to know that there are different types of current electricity. So generators produce electric current as a coil of wire that moves through a magnetic field. We're going to come back to this when we get to magnetism, but you just need to know that magnetism and electricity can work together hand in hand. But when you have a generator, as that coil rotates, the direction of the electric flow can reverse. So when the flow of electricity reverses or changes, we call this alternating current or AC current. And you'll need to know that AC current is used a lot in a lot of different real life examples. So buildings are powered via AC current. So here's an example of what AC current looks like. So you can see the flow of electricity changes direction every now and again. So this is a a good visual representation of how alternating current works. It is a lot more complicated than that, but if you want just a simplistic view, there you go. All right, so let's talk about batteries just a second, because batteries are pretty simple ways that we can get electricity or electrical flow. So batteries can produce an electrical current from chemical reactions. And we kind of touched on this a little bit in lesson 2, where we talked about how energy can transform. So a battery just, not in use, has potential energy, but once we put it in a device and we turn that device on, that kickstarts a chemical reaction inside of the battery that sends out electrons. And so when those electrons start to move, that generates electricity that will power light bulbs or radios or whatever, cell phones. So batteries, because they produce a one directional flow of electricity, we say that they are examples of DC current or direct current. So in direct current, we have electricity flowing in only one direction. So you can see that in this animation here. It doesn't alternate, it just flows in one continuous current. If we were going to graph what alternating current looks like versus direct current, so if you look at the top graph, we have a transverse wave here. It changes. So we see the crest of the wave, and then the trough of the wave, and then the crest of the wave. So it goes up and down, up and down. This is a graphed example of what alternating current looks like. And then in the second picture, we have just a continuous flow of electrical energy. So this is what, if you were to graph what DC current looks like, this is it, just sort of a flat, constant, continuous line. So what I want us to do is sort of do a little bit of research into how we actually get our electricity that powers our cell phones or our lights or our televisions. So you probably have wondered before, like, how do I just turn on a switch and then magically my computer comes on? Or I can plug in my cell phone and magically it just gets the electricity it needs. It's not really magic. There is quite a bit that goes into it, but I want you to pause the video. If you're watching this virtually, I want you to pause the video and just do a quick Google search of how we get our electricity. And I want you to, on the back of your notes, just create a little diagram or illustration that shows, like, where does our electricity come from and what happens to get it to our homes or our school or our businesses. So do that now. All right, so this is quite a process, and we are going to talk about this process in a lot more detail when we get into nuclear science, which will be in our chemistry unit. But basically, most of our electricity, I know our electricity here where I live, comes from nuclear power plants. Now, there are other ways. You can have hydroelectric power plants. Depending on where you live, you can have solar energy. But a lot of what we have here in the United States comes from nuclear power plants. So these nuclear reactors use nuclear fission to generate enough energy that it moves turbines. So we can see in the picture, number 1 represents that nuclear energy that creates enough energy to power turbines, which turn. And we can see that in number 2, that's a form of kinetic energy. And then when those turbines turn, that generates electrical flow or electrons moving. So that's happening in number 3 and number 4. And then when those electrons start to move through transformers, and then from transformers into our homes and businesses and schools, then we have electricity. So that's just like the quick and dirty version of how we get our electricity. Again, it's a lot more complicated than that, but we will do a lot more research into this when we get to nuclear energy. All right, measuring electricity. This tends to be one of the harder concepts when we talk about electricity, but I think you'll catch on, and I think it'll be simple for you. So I want you to take a second and look at this picture, and I want you to try to create a definition for voltage, current, and resistance based on what you see in this picture. So pause the video now and try to come up with your own definitions for each of these terms based on what you see. All right, so if you are in class with me, we're going to watch these videos. If not, we're just going to continue through the lesson. You'll be able to understand it without watching the videos. But if you feel like you need more information, if you'll just visit YouTube and just type in measuring electricity, you can see there's tons of videos that'll explain this more in depth. So electricity can be measured in 3 different ways. We can measure current, we can measure resistance, and we can measure voltage. So a couple of things you need to get in your notes. Electric current is similar to the way a river flows. So electricity, we use current, which is strange, but we use the letter I to represent current. So in just a minute, we're going to get a new formula. You're going to see the letter I. Don't be confused. That's just representative of current. So current's a measure of the amount of electrons transferred over a period of time. And these electrons are going to move through a conductor or conductive material such as a metal. And then amps is the unit that we're going to use for current. Voltage is a force, and it's a force that causes charges to flow. So if you like to think about it as like a pressure or a kickstart, I'm going to go back to this picture because you can see it visually here. So voltage just gives that current the kickstart that it needs to start flowing through the conductor. Our unit for voltage is going to be volts, and we can just abbreviate that with a capital V. We also are going to have to find and calculate resistance. So you need to know that resistance is the tendency for a material to oppose the flow of electrons. Think friction. And we know that friction generates heat. So this is what makes electricity sort of dangerous because we don't want too much friction. We don't want too much heat. Now, the unit for resistance is going to be ohms, and sometimes you will see it with this Greek horseshoe symbol. So I just wanted to show that to you. And you need to know that conductors have less resistance than insulators. So conductors, one of their characteristics or properties is they allow electricity to flow easily through them, creating less resistance. All right, so here's our new formula. Voltage equals current times resistance. And remember, if you use the pie chart with me, you know that horizontal line that divides voltage by current and voltage by resistance is the division line. And the vertical line that separates current and resistance is the multiplication line. So anything that crosses the multiplication line, you're going to multiply. Anything that crosses that horizontal line, you're going to divide. So we have several different formulas that we can get from this one concept. And so I've got those on the screen because sometimes you're going to solve for resistance, sometimes you're going to solve for current, and sometimes you're going to solve for voltage. All right, so let's look at this first example. If I were to ask you what's the resistance of a circuit, if the current's 4 amps and the voltage is 12 volts, you could easily figure that out. So I'm going to go back to the formula. We're looking for resistance. So resistance is voltage divided by current. So the voltage is 12, the current is 4, and 12 divided by 4 would give me 3. Do keep in mind that the unit for resistance is ohms. So you can either use the Greek symbol or you can write out ohms, but you do need to make sure that you have units when you work out these problems. Right, so now we're going to do some Ohm's Law practice problems. Hopefully your teacher has given that to you. If you're in class, then you have already been given this. So work on those problems and then we'll go over the answers. All right, once you finish the Ohm's Law worksheet, we're going to jump into parallel circuits and series circuits. So one more time, remember a circuit is a complete closed pathway for electricity to flow. And we have two different types of circuits. So you can have a series circuit, which is only one path that electricity flows in. So if you see here, we have our voltage source, which is the battery, and electricity is flowing from one end of the battery through all three light bulbs to the other end, and that's continually cycling. So we have one path that electricity flows in. So this is what we call a series circuit. Now, in a series circuit, the voltage is going to be divided amongst what we call the load. So assume here in these pictures that each light bulb is going to be considered the load, and they have the same voltage, the same wattage. They do not have the same voltage, though. So we can see in this first picture that our power source is 120 volts. And we have one light bulb. So what happens here is each light bulb is going to get the voltage divided. Since there's only one light bulb, it gets the full 120 volts. However, if we were to add a light bulb to this circuit, then each light bulb will not receive 120 volts. It'll be divided equally. So 2 light bulbs will receive 60 volts apiece. If I were to add a third light bulb, can you figure out how many volts each light bulb would receive? And if you said 40, you would be correct. So 3 light bulbs, 120 volts, it would divide equally. So for every light bulb that we add, each light bulb would receive less voltage because the voltage is going to be divided amongst the load. Now, we can also have parallel circuits, which means that we have alternate paths or branches for electricity to flow. So if you look at this picture, we have colored electrical electrons that show the different paths that electricity can flow. So what happens here is if one of these light bulbs were removed, it is very likely that the other 2 light bulbs will remain lit because there are alternate paths for electricity to flow. So here we see 3 different paths that electricity can flow. Now, in a parallel circuit, each load gets the full voltage. So if I have 120 volts coming from my power source and I have 3 light bulbs, all 3 are getting the full 120 volts. If I were to add a 4th light bulb, it would also get the 120 volts. If I were to remove a light bulb and only have 2, both still get 120 volts. So each load is going to get the full voltage in a parallel circuit, whereas in a series circuit, that voltage gets divided. All right, so now you have a series and parallel circuit practice activity. Pause the video now and go ahead and complete that.